Welcome everyone, and thank you for joining us today for DigitalGlobe's lead webinar series, Learn, Engage, Act, and Discover. My name is Becky Schneider, and I'm the Marketing Programs Manager at DigitalGlobe, and I'm also going to be your host for today's webinar. But before we get started, I want to pass along a few tips to everyone to keep in mind while viewing today's webinar presentation. First, all attendees are on mute. To ask a question, please use the Q&A chat box feature that's located at the right-hand side of your screen. All questions will be answered at the end of today's presentation. The audio for today's presentation is only available via your computer speakers and not the phone line. And lastly, a link to today's webinar recording will be sent to everyone via email within the next 48 hours. Today's webinar will be presented by Harris Corporation and is titled Capitalize on WorldView-3 SWIR Data with ENVI. There are a multitude of applications for WorldView-3 because of its ability to collect data from both the visual spectrum and the infrared spectrum. Today's webinar will highlight how the 8 bands of shortwave infrared, or also known as SWIR, information can be collected by WorldView-3 and can be exploited using ENVI image analytics. Today's webinar is going to be presented by Matt Hallis. Matt is a technical solutions engineer at Harris and has been with the company since 2012. Matt has a strong passion for the environment and enjoys helping customers understand how remotely sensed imagery can be used to monitor the planet and assist with pollution and environmental degradation mitigation plans. Matt graduated from the University of Denver with a Bachelor's of Arts in Geography and Environmental Science. Outside of work, Matt is frequently found in the mountains of Colorado, hiking, skiing, rafting, and camping. So without further ado, I would like to welcome Matt, and let's begin today's webinar.
Hey, thanks a lot for that introduction, Becky. Hey there, everyone, and welcome to the webinar, Working with WorldView-3 Shortwave Infrared Data in ENVI. This presentation will focus on using the image processing software ENVI to visualize and analyze DigitalGlobe's WorldView-3 shortwave infrared data. SWIR data allows the user to visualize features not visible to the human eye. The data that is used in this webinar is provided by DigitalGlobe and is for educational purposes only. During its 120-year history, the Harris Corporation has transformed communications and information technology from the early printing press to the space age and to today's fast-paced digital age. Since its beginnings, it has focused on providing innovative, reliable solutions that connect, inform, and protect the world. There are various business segments which comprise the Harris Corporation. The image processing software ENVI is based out of the Geospatial Solutions Group, focused on providing actionable intelligence to users across all industries, including the defense and intelligence sector, agriculture, oil and gas, federal and county governments, and many more. Getting good data is important, but at Harris, we know that the ability to turn that data into useful products is essential and often the biggest challenge. Whether you need high-quality elevation models, high-resolution imagery, fast turnaround data deliverables, or analyses that provide actionable information, we have you covered with our unmatched geospatial data and image processing capabilities. Listed on the screen is the agenda which we will cover today. First, we will cover a quick background on the electromagnetic spectrum, then turn our focus to industry applications of shortwave infrared data. Next, we will open and display WorldView-3 shortwave infrared data in ENVI, then view apparent surface reflectance for various features in the scene, and collect training data for the purposes of creating a final land classification product. At the end, we will leave some time for a question and answer period. Becky was already kind enough to give me a quick introduction, but on this slide you should see my email listed. I encourage you to reach out to me with questions regarding ENVI as it pertains to SWIR data and any other questions you may have. This infographic shows the spectral resolution of the multispectral bands captured by WorldView-3 along with the SWIR bands. For the purposes of this webinar, we will mainly be focusing on the SWIR bands, but know that combining both of these products, the multispectral and the shortwave infrared, will vastly increase your understanding of your area of interest. Being able to view the surface reflectance values beyond the near-infrared range allows the user to see many absorption features and spectral features that are otherwise invisible to most commercial sensors available today. The ability to detect photon emissions in 8 distinct spectral bands in the shortwave infrared with high spatial resolution is a benefit found solely in WorldView-3. Visible light is the portion of the spectrum humans can sense with their eyes. This small range is roughly 400 to 700 nanometers, with violet being the shortest wavelength and red being the longest. Within infrared light, there are several divisions or classifications. Immediately adjacent to visible light is near infrared, within the 700 to 1400 nanometer range. Shortwave infrared, SWIR, is adjacent to NIR and refers to non-visible light falling roughly between 1400 and 3000 nanometers. We will be working with shortwave infrared data, which allows us to detect the presence of features not visible to the human eye. Every surface or object absorbs, emits, and reflects light uniquely depending on its chemical makeup. Chlorophyll in plants absorbs red and blue light, but reflects green and infrared. This is why leaves appear green. The unique absorption and reflection pattern is called a spectral signature. Identifying the absorption features in the infrared region of the spectrum is what allows us to delineate between materials. If you were to have a sensor collecting radiance or reflectance readings in just the visible range, you would not be able to detect the difference in the features. Once you have the added spectral resolution of the shortwave infrared range, 1.4 micrometers to 3 micrometers, the difference in spectral signatures between soil and senescent vegetation is very apparent. As you can see in the spectral profile on the plot, in the visible portion of our spectrum, we cannot see much change between the soil, which is our red profile, and the decayed leaf, which is our green plot. However, once you get to the shortwave infrared range, roughly 1.5 micrometers to 2.5 micrometers, the difference in the reflectance profiles is extremely apparent. A spectral signature of an object is a function of the incidental electromagnetic wavelength and material interaction with that section of the electromagnetic spectrum. Elements, molecules, and even cell structures have unique signatures of reflectance. Identifying the presence of various spectral signatures can give high confidence that the currently viewed pixel contains your feature of interest. What we see in this slide are spectral signatures of Earth features. However, this only covers the visible portion of the electromagnetic spectrum. It is when we can use the shortwave infrared portion of the spectrum where we start to see additional spectral features. So why SWIR? Many materials have specific reflectance and absorption features in the SWIR bands because of their chemistries that allows for material detection and identification. Examples include minerals used in mineral exploration, urban features such as roofing and construction materials, vegetation, petroleum, and a variety of other man-made chemical compounds. Analysts can examine the unique patterns of absorption and reflection and use this information for material identification. As you can see in the reflectance profile on the slide, there are clear and distinct attenuations on the profile, deemed absorption features, which are only apparent in the shortwave infrared region. Having the added clarity allows for material distinction that would not be possible solely with visible or near-infrared data. Listed here are the commercial and government satellites currently collecting SWIR data. A point of note is that amongst commercial and government satellites, WorldView-3 boasts best-in-class spatial and spectral resolution in the shortwave infrared portion of the electromagnetic spectrum. WorldView-3 is the first commercial satellite to have 8 high-resolution bands that capture information in the shortwave infrared regions of the EM spectrum. WorldView-3 expands deeper into the infrared spectrum than any other commercial imaging satellite and provides rich data for precisely identifying and characterizing man-made and natural material, penetrating smoke, and mapping minerals. The 8 SWIR bands span the spectrum's 3 atmospheric transmittance imaging windows to capture unique information for agriculture, forestry, mining/geology, and other applications. The pixel size for SWIR data collected by WorldView-3 is 7.5 meters, and the spectral range covered is 1195 to 2365 nanometers. When downloading WorldView-3 data, you have the option of acquiring panchromatic imagery, multispectral imagery, and shortwave infrared. The ENVI software can work with the WorldView-3 data stack in a seamless manner, allowing the user to work with all of the data available in a very efficient manner. When you combine all of these data products, you have extremely powerful information that can be exploited easily and efficiently using the ENVI suite of tools. Multispectral, panchromatic, and shortwave infrared imagery has different spatial resolution, and as a result, these data products are downloaded as separate files through DigitalGlobe. ENVI can easily layer stack these separate files into one data supercube that will allow the user to have access to the full spatial and spectral resolution offered by WorldView-3, but in one easy-to-use file. The data manager in ENVI is shown on this slide. Look at the figure. This is how ENVI organizes and displays spectral data. The fact that the median wavelength of each spectral band is listed in parentheses next to the band name/band number is extremely useful when creating band composites. So what exactly can we accomplish with SWIR data? The analysis of SWIR data has applications in agriculture, forestry, geology, hydrology, coastal resource mapping, and environmental monitoring, to just list a few. SWIR data is especially useful when differentiating between senescent plant canopies and bare soil. Look at the slide we have on the screen. Our top figure is a true color composite taken over cuprite hills, and the bottom is a false color composite of the exact same extent, but this was created using shortwave infrared bands to colorize the image. Note the added range of hue, saturation, and light in the second figure. Oftentimes, a false color composite image will help highlight materials that would not be apparent in a true color composite. So we now turn our focus to vegetation and remote sensing. A healthy leaf structure will efficiently scatter near-infrared wavelengths, which is why collecting imagery in the near-infrared region is essential when analyzing vegetation. When viewing the reflectance spectra for vegetation, in the visible range is where you can identify changes to the pigment. Chlorophyll A and B increase in healthy plants, meaning healthy plants will appear greener. Carotenoids increase in senescent or dead vegetation. These will appear more yellow in color to the human eye. Although being able to decipher small absorptions in the visible range can help you approximate the health of vegetation, it is when you get beyond the visible portion of the electromagnetic spectrum where differences in plant health become quite apparent. Identifying the water content of vegetation is essential to understanding the health of the plant and its progression in the growth cycle. Water absorptions can be identified mainly in the near-infrared and shortwave infrared regions. Carbon in the form of sugars, starch, cellulose, and lignin display features in the shortwave infrared. Finally, some proteins with nitrogen have features in the SWIR range. And SWIR data can also better penetrate canopy shadow to identify features not typically seen by most commercial sensors. At this time, we have covered a sufficient background on SWIR data, and we will now turn our focus to working with WorldView-3 SWIR data in ENVI. So after covering a decent background on SWIR data, we're going to turn our focus to using shortwave infrared data within the ENVI interface. Now, one of the first things that you always do whenever you're performing an image analysis is you want to investigate your scene. ENVI makes this extremely easy because when you load up shortwave infrared data, automatically ENVI will display the first band as a grayscale image. This is the default ENVI action, and this is because our shortwave infrared data does not contain any visible spectral bands. If we did have spectral bands that covered the red, green, and blue bands, then we could choose to colorize our scene using a true color composite. However, given this data set, we want to investigate each band one step at a time. Now, satellites carry many sensors, each tuned to a narrow range or a band of wavelengths. And viewing just one of these bands is a bit like looking at the world in shades of gray. The brightest spots are areas that reflect more of that wavelength of light, and darker areas absorb in that wavelength, while gray areas scatter, absorb, and or reflect to different degrees. The focus of much of image analysis is identifying the varying degrees of reflectance and absorption to help you identify features and eventually classify pixels. So what we want to do is we want to animate through these bands because we want to start to identify if any of these specific bands correlate with a specific feature type. Recall that our first band being displayed is the near-infrared 1 band or shortwave infrared 1 band contained within the SWIR dataset. ENVI allows you to really easily investigate what the band you have loaded is by either double-clicking on the file and viewing the metadata, or simply hovering over the band name or the band name in the layer manager. We can see that this band is roughly at the 1200 nanometer range. So we want to animate through these bands and try to identify if a pixel correlates with a certain feature type, certain pixel values correlating with feature types. So we right-click on the file in the layer manager and select band animation. This is new functionality that is extremely useful if you work with superspectral or hyperspectral data sets. Oftentimes, you want to play through all of your bands to try to identify certain bands of interest. This dialog is easy to use. I can play forward selecting these buttons, the play forward, and then I can play backward selecting the play backward button. I can adjust the speed with which I animate through my band by adjusting this drop-down. Furthermore, when you're working with a very large spectral data set, it's often beneficial to display the band number that you're currently viewing. So I can select the options drop-down, annotate, and then select frame number. Now I have an annotation within my ENVI displays that shows exactly what band I have currently displayed. Like I said before, we want to start to identify certain pixels that have high pixel values with a certain band. If we navigate to the southwest of our image, we should see a golf course, or what appears to be a golf course to our trained eyes. It appears as though the vegetation contained in the fairways has very high reflectance values in this first band, which makes sense because due to the aforementioned fact that healthy leaf structure will scatter near-infrared light in particular. And this tool was developed to allow the user the ability to play through their spectral bands sequentially. The goal of animating our bands is to try and see if any of our bands seem to highlight certain feature types with bright pixel values. Recall that a bright pixel in a grayscale image simply means that the pixel has a high reflectance value in the wavelength currently being displayed. Oftentimes, though, it's really difficult to see a lot of differences in contrast using a grayscale image. So instead, we can display a color table so that we can really start to add some contrast and identify discrepancies between our bands and pixels. I can right-click on my file in the layer manager, select Change Color Table, and I'll choose a rainbow color. Now, as I play through the bands, this added color context really allows me to see how certain pixel values differ in certain spectral bands. Turn your focus to the northwest portion of the scene. This is where we have a large industrial area. It appears as though in the lower order bands that all of these rooftops have similar pixel values. However, Once we get to the higher order bands, we start to see clear and distinct differences. If we look here in the rooftops around where my mouse is currently hovering, we have some green rooftops and some red rooftops. Recall that we are currently viewing band 8. If we then change this so that we are viewing band 6, we start to see that the previously green rooftops are now in fact red. This harks back to one of the essential facts of why you would want to use shortwave infrared data. Oftentimes, synthetic materials can be differentiated quite easily in the shortwave infrared range, and that is because synthetic materials have extremely high reflectance values still out in the shortwave infrared range, whereas natural materials will not have a high reflectance out in the shortwave infrared. Oftentimes it can be beneficial to display this color table, but what's even better is that WorldView-3 allows you to display a multispectral image if you choose to collect that data as well. We will close out of our band animation file, zoom to full extent, and then load up our true color composite. Natural color, also called true color, uses red, green, and blue. This true color image combines actual measurements of this red, green, and blue light, and the result appears as what a human would see from an aircraft. I will brighten the image using a linear 5% stretch. Now I can start to zoom into an area and adjust my transparency to see what the true color looks like, but also to see what my image appears underneath. We are seeing that, yes, just as we thought, a lot of the grass surrounded by this golf course has extremely high reflectance values in this shortwave infrared 1 band. Now, oftentimes it's useful to display a color composite that is not in fact true color. And since we have shortwave infrared data, it is in fact impossible for us to display a true color composite with the shortwave data because, as I said previously, we do not have bands that cover the visible range for that file. So oftentimes people will use a false color composite. A very common false color composite with multispectral imagery is a composite near infrared that colorizes your near infrared band as red, your red band as green, and the green band as blue. We can display this color composite extremely easily from the ENVI interface by right-clicking on the file in the Layer Manager, selecting Change RGB Bands. We then select our near-infrared 1 band as red, our red band as green, and we color our green band as blue. Once we hit select, the image will load. I'll reduce our linear stretch to a 2% so the colorization appears more natural. What we have done now is we have colorized our near-infrared band as red, meaning all of our pixels which contain vegetation should appear red. And the pixels that contain more natural or unnatural materials and synthetic materials should appear potentially more cyan in color. Just as we expected, all of these bare areas of vegetation have extremely red pixels. When we then turn off this layer in our Layer Manager, we see that similarly, those pixels are white or extremely bright in the grayscale image. So we will now display a false color composite using our shortwave infrared data in an attempt to identify discrepancies between synthetic materials. What we have on the screen is similar to what we had in the previous ENVI. On the left, we have our true color composite. On the right, we have a false color composite. In ENVI, I can expand the files in my Layer Manager to see exactly what bands I have displayed as what colors. To create the false color composite of our shortwave infrared file, I have displayed SWIR 7 as red, SWIR 1 as green, and SWIR 5 as blue. This is a common band combination for WorldView-3 shortwave infrared data because I have colorized vegetation green. Oftentimes, it is beneficial to try to colorize a near-infrared band as green as humans can perceive vegetation and start to understand what they are seeing in this image a little bit better. So let's turn our focus once again to the industrial area we saw in the northwest region of our scene. Recall that we mentioned how band 6 and band 8 seem to provide good discrepancies on rooftop types. This example right here will get at the core of why using shortwave infrared data is so beneficial. In the true color image on the left, it appears as though the white roofs could all be the same material. However, when we look at our false color image on the right, it's quickly evident that these rooftops are made of different materials. Take a moment to consider what the colors mean in our false color image. A pixel appearing more green has a higher reflectance value in the shortwave 1 range. A pixel appearing more blue has a higher reflectance around 2165 nanometers. And the magenta pixels have a high reflectance in the blue and red range, which are 2165 and 2260 nanometers respectively. Just by using our eyes, we could identify that these roofs are made of different materials. That is, if we have our shortwave infrared data. But what if we just had our multispectral data? By our eyes, it seems as though, yes, in fact, these are the same materials. We can display a spectral profile to confirm what the reflectance data looks like in each of the different roofs. I will display a spectral profile of my true color and of my SWIR file by right-clicking on the files, selecting Profiles, and then Spectra. Since I have linked my views, I know that I am going to be zoomed in on the same exact pixel. You do need to keep in mind the fact that our pixel sizes are different. What we start to see in our spectral profiles is the reflectance value given for the currently selected pixel. In each of these files, we have 8 distinct pieces of information, and we can go to each of these pieces of information because that is what each band contains. I can collect multiple pixel spectra in a spectral profile in ENVI very easily by holding down my Shift key. If I hold down Shift and select the other rooftop, which appears white in the true color, but different color in my false color composite, then we start to see exactly where these differences occur. The spectral profile on my left makes it seem as though we are just simply varying our reflectance values in terms of brightness. And many classification algorithms would in fact classify these materials to be the same material. However, when we look at our shortwave infrared data, the difference in material type is extremely apparent. So at this point in time, we will turn our focus to collecting training data for the purposes of creating a land classification product. What's extremely beneficial about this WorldView-3 sensor is having the multispectral imagery, which can add context to our shortwave infrared imagery. So what we want to do right now is to start to collect some pixel spectra that will represent pure examples of a feature that we are attempting to classify. I will remove both of my views so that I'm left with just one view, and then I'm going to load my true color composite underneath my shortwave infrared file. Now, whenever I fly to an area within my scene, I can zoom in to this area and use my image manipulation techniques to see what the human eye would perceive. As I move my transparency slider, I can start to see exactly where the fairway ends, where the cart path begins, and where a little river or canal network runs in the middle of this area. With the multispectral file below our SWIR file in the layer manager, we can use this transparency slider to see the true color imagery underneath the SWIR data. The added context provided by the natural color imagery and with higher resolution pixel size makes it possible to closely inspect the pixel we are selecting as grass. What's really nice is that as my transparency is turned up to 100, I am just viewing the true color. Although, as you should be able to see, as I select different pixels in my shortwave infrared, the pixel size is clearly larger than a single pixel for the true color. That is because I look at my spectral profile and I am displaying the SWIR QAC file. QAC is indicative that this file has been atmospherically corrected via the Quick Atmospheric Correction module available within ENVI. What we want to use this multispectral imagery for is to make sure that when I choose an example pixel to use as training data, that I do not collect a mixed pixel. It appears as though we have some golf carts in the scene, some shadow, some tree, and this canal that we mentioned previously. Being able to ensure that we just select the most pure example of our feature will ensure that our classification is the best possible. So after selecting the pixel that will be used as the grass end member, we can easily clear what we have currently displayed. Based off of the transparency slider, I can see that I'm picking a pixel that has an extremely high reflectance in the near infrared 1 band because it is colorized green in my false color composite, but also that it does not contain any of this cart path. In my spectral profile window, I would simply expand the panel, select my curve option, and double-click my name to change the name of my training data to represent the feature I am attempting to classify. I can change my color extremely easily as well. Oftentimes, when collecting training data for classification, you want to have kind of a safe haven to collect all of your pure examples of training data. The way that I do this from ENVI is I select Options, New Window with Plots, and that will push whatever plots I have currently displayed in my spectral profile window to a new ENVI plot window. Now, as I select on different pixels within my scene, I can maintain the pixel I have collected in this ENVI plot, but I can still view what the new pixel I have selected looks like in my spectral profile window. In a real situation, we would repeat the same process for as much training data as we wish to collect. However, in the interest of time and displaying a final result, we can load a spectral library file created previously, which contains the training data we will use for classification. We will be using the spectral angle mapper algorithm to perform image classification. Once you have collected a lot of these spectra, then you would simply expand your toolbox and double-click on the tool titled Spectral Angle Mapper Classification, and then load your training data from there. In the interest of time, we've already done this, so we will snap to our completed product. Spectral Angle Mapper was selected because it deals with shadows and brightness differences extremely well. If we zoom into our area, with our multispectral file underneath, we could use our transparency to inspect our results. Recall the rooftops that we looked at previously, found right here in the middle of the scene. We can see that, in fact, ENVI classified the rooftop on the right as asphalt and the rooftop on the left as another white roofing material. We can also see that the solar panel was extracted extremely well from the center of this image. If you look, you can see that vegetation was pulled out, and the bare soil and vegetation was delineated extremely well. At this point in time, we have completed our demonstration of how to work with SWIR data within the ENVI interface. So I would ask you to please ask any questions that you feel right now.
So thanks, Matt, for your very informative presentation. At this time, we're now going to take some questions from our webinar attendees. So welcome again, Matt. I had some questions that came in during your presentation. One of those questions is a listener would like to know, can we get multispectral and PAN and SWIR data used in this webinar?
Yes. To answer that question, you absolutely can. We have actually a computer-based training that is on the excellusviz.com website. It's in the Learn tab of our website. And basically, you just go there. As long as you have an excellusviz.com login, then you will have access to download the data that was used not only in this webinar, but we have a full comprehensive training that will teach you kind of hands-on, step-by-step, how to use SWIR data in ENVI.
Perfect. Another question that came in is a listener would like to know, how does ENVI work with ArcGIS?
Well, we actually have a number of interoperability features available between ENVI and ArcGIS. We have a platinum partnership actually with ESRI, which allows us basically to work with their engineering team as they're developing their next iteration of ARC, so that every time ARC is updated and ENVI is updated, all of those interoperability features will be available. We have an ENVI tools for ArcGIS, which is basically a small subset of the spectral analysis tools available within ENVI that are available directly from the ARC interface. And furthermore, we also can easily move files in between ARC and ENVI. Native ENVI files can be opened easily in ARC. Shape files can be opened very easily within ENVI and then edited as well to your choosing.
Another question that came in from a listener is they made a comment that they're a federal government employee, and they're curious to know if they can acquire this image through the NextView license.
I would probably have to direct that maybe back to you guys. I'm unsure as to how the NextView licensing works in regards to federal employees.
For the person who answered that question, I'm going to put my email address in the chat box, and you're welcome to email me, and I will put you in touch with our on-site DigitalGlobe employees who are responsible for that NextView contract.
Hey.
Another question that came in, Matt, is a listener would like to know if you can provide an example of a use case of ENVI that's being used to solve a problem with SWIR data.
Yeah, absolutely. We actually have, we focused a little bit on material distinction and kind of synthetic material distinction, and actually first responders to a lot of wildfires out in the West have been using ENVI software to basically classify the different roof types that they have in fire-prone areas so that they can have a good idea of potentially what areas might be more prone to being set on fire by a nearby blaze. I thought also I'd quickly respond. I saw a few questions just regarding kind of more functionality of like radiance and using atmospheric correction. It seems like some people just want to know, typically you would perform radiometric calibration when you get raw imagery from DigitalGlobe, and then you would perform the quick atmospheric correction, and that is what we did actually in this webinar, just so you guys all know. So there was nothing kind of going on behind the scenes.
Great. And another question that came in, Matt, is a listener would like to know how long is the time between the image capture and the final user release? He said, you know, regarding your environmental disaster or high-resolution spatial images, could be useful as soon as possible.
Right, of course. I do know that WorldView can be tasked. So oftentimes in times of issue, times of disaster, that people can afford to task WorldView-3 or WorldView-2 to a certain area. But I think I would have to turn to you guys to know exactly what the actual download time is from positioning the satellite to getting the data.
Another question that came in, Matt, and I may refer this question to our research scientist who's here with me, Bill Baugh, but a listener came back and was wondering why the SWIR 7.5, why is SWIR at 7.5 meters and not the 3.75 as it was previously announced? So Bill, did you want to answer that question?
Sure. Yeah, this is Bill. So SWIR data is collected natively at 3.7 meters by the instrument, but our government license currently limits us to distributing it at 7.5 meters, and that's still being evaluated whether we'll be able to distribute at native resolution or not, but that's yet to be determined. So we're currently limited to 7.5 meters.
Another question that came in is a listener would like to know, in what areas does DigitalGlobe WorldView-3 data surpass hypospectral imagery data in terms of target identification of synthetic materials?
A big point that we like is the higher resolution and the better tasking ability. Oftentimes, hyperspectral sensors have extremely large spatial resolution, so the increased spatial resolution of SWIR and the ability to task that really helps with this material identification.
Moving on, another question that came in is, have either you, Matt, or Bill seen any examples of differences of weathering of rocks or minerals determined using ENVI and WorldView-3 data?
Yeah, Bill, would you like to handle that, or would you like us to?
Well, I think the question is there have we been able to see a gradient of weathering using the WorldView-3 data?
Mm-hmm. And ENVI.
Yeah, and I haven't been able to see a gradient of weathering yet, but then I haven't gone after it either. It seems like the kind of thing one would need to start with a little bit of ground truth to be sure that they understand what's happening. It'd probably take the form of reduced depth of absorption features that are observed. What do you think, Matt?
Yeah, that's really what we were thinking as well, so I appreciate that.
So we're going to continue to take a couple more questions before we close out today's webinar. Another question for you, Matt, is what kind of tools do you have to work with? What kind of tools do you have to work with for the other spectral bands of WorldView-3?
Oh yeah, so we have a large number of spectral indices, vegetation indices. We actually wrote about 6 specific WorldView-2 indices, so we'll be working similarly on WorldView-3 indices, but a lot of our spectral analysis tools like our synthetic mapper, angle convex cone, that can work really well with this WorldView-3 data. We have a lot of spectral unmixing algorithms that can help with your material identification and detection. So there's a lot of different tools that we offer. Change detection is oftentimes used, so many different options.
And I'd like to throw something in there too. I really like the band map tool. So by inspection of the data, if there's a spectral shape or a spectral feature I've observed that I want to highlight, I can write my own indices to highlight that even better. So it's a simple approach that can be leveraged with that band map tool.
Exactly, Bill. I mean, oftentimes you guys on the project science side did really great jobs, obviously, of identifying the spectral ranges to be covered by these satellites. So then having the ability to basically on the fly decide how you want to exploit that is a really big point of ENVI and why a lot of folks decide to use our software.
Moving on, I see some of in the chat box, there's been a couple of questions in regards to WorldView-4, and if we have any additional information to share about that satellite. The only information that we do have is what has been publicly announced, and that is that we are launching in 2017. At this time, I don't have any updates regarding WorldView-4, but stay tuned and watch the DigitalGlobe.com website, and that's where the updates will be posted first. Moving on, another question that came in is a listener would like to know, is there a reason why WorldView-3 data cannot be atmospherically corrected with flash, only with QUAC?
Oh yeah, so our next release, 5.3, ENVI 5.3 Service Pack 1, will allow you to perform flash with WorldView-3 data.
Great, thank you. Another question is, Alyssa would like to know, is SWIR appropriate for flood mapping?
Yes, absolutely. SWIR, one of the big points that SWIR helps with can be with delineation between actual land and water, but then also the content of water in soil. So basically, there's a lot of material on the DigitalGlobe website, but then also I would really suggest looking at some of NASA's materials regarding using shortwave infrared imagery for flood mapping. There's abundant information.
Another question that came in for you, Matt, is they'd like to know how many or what classes were you able to distinguish with SWIR alone?
Well, typically a rule of thumb in remote sensing is that you really do N bands minus 1 N bands plus 1 is your classification. So for us, we have 8 spectral bands. That would lead most people to believe that you can get about 9 good classifications out of that. For our purposes, we only focused on about 6 or 7, but what I did want to note is that we actually classified that entire scene with literally 6 total pixels. We used 1 pixel for each class. So if we had wanted to extend the quality, make this a really good classification, we could have been in that 8 or 9 range. But really, what you can extend beyond that N plus 1, but then you start to stretch the ability of the data. But I definitely have seen classifications with 15 or 20 using just 8 spectral bands.
Another question that came in is, Alyssa would like to know if WorldView-3 SWIR can be used for shallow water vegetation mapping.
My thought at first would probably be utilizing the visible and the near infrared because first off, it penetrates water well, but also you have the added benefit of the spatial resolution, which oftentimes in those kind of coastal mapping areas, it is beneficial to have a smaller pixel size.
Yeah, Matt, I would agree that the shortwave bands really only penetrate centimeters or millimeters, essentially not at all in the water. So if we're trying to look at subsurface features, even in shallow water, you're really not going to get much from the SWIR bands.
Nice. Thank you, Bill.
But then conversely, the blue will penetrate about as far as you can see, up to about 30 meters. So like you were saying, the coastal blue, green are really the way to go for shallow water.
Nice.
Moving on, and this could be either for you, Matt, or Bill, and Alyssa would like to know if either of you have done much work utilizing the full set of 16 bands.
Yeah, so I could take a first stab. We can actually layer stack files in ENVI and make what we deem a supercube. We can do that really easily, basically. You choose the pixel size that you want. So typically what you'll do is you'll use the largest pixel size of all the files that you have available. But basically we can combine our multispectral and our SWIR. And actually I did it somewhat in the webinar. I had them as separate files, but oftentimes I'll use that transparency slider when performing a land classification or material identification, so I have the added spatial resolution, but then also the spectral of the SWIR. So that's, I use it pretty often, but Bill, maybe you have some thoughts as well?
Yeah, I'll jump in with that too. I build supercubes regularly by stacking the 8 veneer bands and the SWIR bands to make a 16-band file, all the same resolution. And just like you were saying, I choose a resolution, whether I want to go to the coarser or the finer, and then resample. And just as a specific use case, iron and steel have an absorption feature that straddles the veneer and SWIR. And so by putting that together, some very clear spectral features start to show up for iron and steel, and if you're looking at rocks, various iron oxides that are important for understanding ore deposits or even acid mine drainage. And those are all enabled by layer stacking the veneer and SWIR together. And it really brings out some opportunities that weren't available with the Astra satellite which had some SWIR bands on it as well, but it didn't have the proper band placement to really leverage these iron absorption features.
Right, and yeah, just to piggyback, the ability to do that layer stacking in ENVI is incredibly easy. Those are the kind of tasks that we definitely, it's not, you can actually automate it if you'd like, but it's very easy to just choose the band, select pixel size, output file name, and you're done.
Okay, moving on. Another question came in. It's in reference to shallow water applications. And the listener would like to know, can you do other corrections such as sunlight corrections for shallow water applications?
I'm not a total expert on that. Maybe, Bill, you have some thoughts?
I haven't worked with the bathymetry and water applications that much, but a colleague of mine has done considerable work. And I'm not sure what corrections he's made. I believe he corrects the reflectance and then can actually do spectral mapping of some general categories subsurface, such as sand, coral, seagrass, for example, and has had some good success with mapping those bottom types as well as generating shallow bathymetry maps as well.
So for the listener that asked that question, feel free to send me an email, and I'll be happy to put you in touch with Bill's colleague if you'd like more information about that. Moving on, another question is, the listener would like to know if there's a geological case study for geological mapping.
Yeah, there's a really large abundance of that. I mean, my first thought, of course, is going to be to look at the USGS. They recently released actually a large number of mineral maps in the Afghanistan region. I know that they spent a significant time working on that. But what you probably want to look at is the USGS Spec Lab. And that's going to give you a lot of good information to begin, and then also maybe some thoughts of research for your own. And then, Bill, obviously, please, tack on to that, because I'm sure you definitely can.
Sure. Something that all the readers or all the listeners can access is online, the Journal of Applied Remote Sensing. There was an article published by Fred Kruse, K-R-U-S-E, this year, that used a Cuprite data set to look at WorldView-3 data specifically relative to mineral mapping performance. So Journal of Applied Remote Sensing, it's online. You can download it for free. Primary author was Fred Kruse, K-R-U-S-E.
Cool.
Okay. Moving on, we're going to take a couple more questions before we close out today's webinar. And there's been a lot of chat being discussed about the CAVIS band. And Bill, I don't know if you want to take this question, but a lot of listeners would like to know when the CAVIS bands are become available and if it's going to be able to help with atmospheric correction in flash.
Yeah, I can address that. So CAVIS is an additional sensor. It's still undergoing calibration, and I have not heard a final date on that yet. So CAVIS data are still not available. The last I heard, as a company policy, the data will not be distributed to users, but instead used internally to improve atmospheric compensation. And so at that point, I guess they would not be available for flash, but instead would be available for atmospherically compensated products from DigitalGlobe. Does that address the question?
Mm-hmm. Another question that came in, a lot of questions starting to come in regards to mineral mapping, and people are kind of curious to know what, with SWIR or ENVI, what type of minerals can you detect? Can you detect copper, gold, clay type of foundations? What are some of the things mineral detections that you can detect with SWIR imagery?
Well, Bill brought up that point of being able to, if you do have that, the veneer as well, to kind of delineate between iron and steel, but also clay is very easily identifiable. There's an absorption feature roughly at about 2,200 nanometers, which can be identified pretty readily with these SWIR bands. And basically, minerals that can indicate elements like gold, but not gold itself.
Yeah, that typically the gold and the copper and the ore deposits that people are going after, you can't see the gold itself. Instead, you have to find clues that it's there. And so, Matt, like you were saying, the clays and alteration products are the kind of things that we can go after. You mentioned the clays. Those come out well. There's carbonate, which are things like limestone, dolomite, that have absorption features that show up. And some of the mica products, like cerussite, can also be identified. What else? Alteration minerals, such as alunite and jarosite, come out nicely. And that paper I referenced just a moment ago actually covers about 6 or 8 categories of minerals that could be mapped.
Yeah, and then, at the end of the day, what really should be done is, take a gander at the USGS, at the spectral libraries that they make available, and whatever you decide to turn your focus to, then basically just look at the literature, see if there are absorption features, spectral features that are apparent in bands that are available within the SWIR data set of WorldView-3.
Yeah, good point, Matt. That's my approach when I'm looking for a new material that I haven't worked with before. I start with the USGS library, resample it to WorldView-3 16-band equivalent, and then look for unique features that I can leverage.
Great.
Well, Matt and Bill, we're going to take one more question. We're getting close to our time running out for this morning, so we're going to do one more question before we close out. And a listener would like to know, Matt, if you work with other types of data other than just the WorldView-3 SWIR.
Yes, absolutely. We work very, very well with actual hyperspectral data. That was really the first realm that ENVI started to really excel in, because it's because of our IDL being an array-based language. Basically, we can process large amounts of hyperspectral imagery extremely efficiently, but also, of course, we can ingest panchromatic, multispectral, so people are starting to deem certain sensors as superspectral. All of that, basically all optical imagery is very easily ingested within ENVI, and then we can ingest LiDAR data as well as SAR data, synthetic aperture radar. So more or less, if you can image it, we can ingest it, and if not, then we'll work on it.
Perfect. Well, that's going to close out the Q&A portion for today's webinar. I'd like to thank Matt, again, from Harris for his very informative presentation. And I'd like to thank everyone for attending today's webinar and submitting your great questions. If you'd like more information regarding the content that was presented today, I encourage you to reach out and contact Matt directly. Matt will be happy to follow up with you offline. Also, I'd like to thank Bill Baugh, again, our research scientist, for helping Matt with some of the technical SWIR questions today. If you have more questions about SWIR and mineral detection, Bill has done several webinars on this topic, and he will be happy to follow up with you offline, and I have included Bill's email information in the chat box feature. So that's going to conclude today's webinar. I thank everyone for attending, and we hope to see you at future events.